This is chapter 9 of the functional programming tutorial, traversable functors. To motivate the introduction of these functors into practice, I always remember the example that you have a list of some data items and you want to process it by using a function like this, where you have a future as a result of this function. And the usual way of doing this in Scala is to use a function called future.sequence. And I have shown this in the previous tutorial. And the idea is that you want to process each element of this list with this function, and you have to wait until the entire list is done. So you have many separate computations for each element of the list, encapsulated by the future for each one of them. And you want to wait until the entire list is done. And basically, this is the type signature that you want in order to implement this computation. You have a list of A, you have a function from A to future B, and you want to get a list of B as a result, and you can get it in the future. So you have a future of list of B as a result. And that is the type signature that the function future.sequence will allow you to have with some work. But in order to understand what this kind of computation does, we want to generalize from a future to an arbitrary type constructor f. And we want to understand what properties these type constructors must have. So instead of list, we have L, and instead of future, we have F. And the type signature of the function is like this. So this function is called traverse. And I believe there's also a future.traverse with a type signature like this that works on sequences. But we want to generalize to some type constructors f and l. And that's what we will be able to do once we understand the properties of this operation. So this operation can be implemented, for instance, if L is this type constructor, then what can we do in order to implement this operation? Well, clearly we have an LA, and we can apply map f. So f is this function. We can apply map f, and the result will be this. Now, in other words, we have not what we want. What we want is FLB, which would be this. So how can we get f of a triple from a triple of f's? Well, clearly, we need an operation that's similar to zip. A zip would be FB times FB going to f of B times B. Now we need to apply zip twice, and then we get from here to here. So once we have the zip, we will be able to implement this traverse operation. That's the conclusion so far. So it seems that f needs to be applicative in order to be able to implement this type signature for at least for this type constructor. So for this type constructor, certainly it is easy to implement if f is applicative. So if it has a zip operation, then we can implement it like this. So that is going to be a fundamental assumption, that for the traverse operation to make sense, the type constructor F must be applicative. Now the type constructor L, on the other hand, we don't know what that is. It could be applicative or not, maybe. We'll find out. But for now, let's say L is traversable if it has this operation. Now in Scala, we have a very limited version of this traverse, which assumes L to be a sequence. So it's not based on this idea of being traversable as such. It's just that one of the properties of a sequence is that you can implement this operation, and we'll see why that is so. But for me, the example with lists and futures, or sequences of futures, is the easy to remember example that helps me remember the requirements for the traverse operation. So I always think that I have a list of some items and the processing makes me a future. So L is a list, F is a future, and then it is clear that I want this kind of type signature. I want to have a single future, and when that future completes, I want to have the entire list of processed data. And that's the easy to remember example. So not the other way around, for example, not a list of futures. I'm not interested in having a list of futures. I want a single future with the final list of the results. And so that's why this example helps me remember this somewhat complicated type signature, where I could easily make a mistake and do A to L of B instead of A to F of B, and LFB instead of FLB. It's easy to mix them up. So remembering this example that I'm starting with, that's what helps me remember the type signature of traverse. So the questions that I'm going to answer in this tutorial, in this chapter, are to find out what functors L can have this traverse operation. To find out if we can simplify this somewhat complicated type signature. Can we express it perhaps through a simpler operation? What are the laws that is reasonable to require for this operation? And finally, to look at contrafunctors and profunctors. Do they have also some kind of analog of this operation? In previous tutorials, I started right away with practical examples of usage. In this chapter, I will first do more theory to understand in more detail and more deeply the properties of this operation. Then it will be easier to follow the usage examples. So, to simplify traverse, we notice that traverse is a kind of lifting of sorts. It's the arguments can be permuted, so these are two curried arguments, so we can take this one as the first argument, and then we have LA to FLB as the second argument. So it's a complicated kind of twisted lifting, and we have seen several times already that often you can find a simpler natural transformation that is computationally equivalent to a lifting. So let's derive that natural transformation that is equivalent to traverse. To derive it, I ask the question, so why can't we have fmap to do the work of traverse? Fmap would have this type signature, and traverse, sorry, this is actually, yeah, so this is the type signature of fmap, but traverse needs FLB here instead of LFB. So, you see, this F needs to be outside, and that's what's missing. So we need to transform LFB with F inside into FLB with F outside. So that's the transformation, that's a natural transformation that we expect to be equivalent to traverse. So let's call this sequence. So this is maybe not a very good name, sequence, kind of suggesting that we change the order of L and F in the functor composition. Not a very good name maybe, but that's a traditional name and I don't know how else to call it. Indeed, we find that the functions traverse and sequence are computationally equivalent. So this is why. Well, we have defined sequence like this. So then traverse of a function f is computed by first doing fmap of f, like we did here. Then we get this. And then apply this sequence function that I abbreviate to seq, which performs this transposition of the order. The type diagram looks like this. So we start with the type LA, and we can do traverse on it directly with this trav function, which takes f and directly gives you from LA FLB. Or you can first do fmap. So you map a function f under L, you get, instead of LA, LFB, and then you change the order. So you reorder the functor composition, LFB to FLB, and the results must be equal. So for any value of this type, you go up or horizontal, and the result must be the same value of this type. That's the definition. And as we have seen before, this pattern applies that natural transformation is defined as a composition of fmap. So sorry, a lifting is defined as composition of fmap and natural transformation. And then this natural transformation is equal to the lifting if you take identity instead of f, obviously. And so then that's a pattern we have seen time and again, where the result is that traverse and sequence are computationally equivalent. You can derive one from the other and back, and you get the same function back. So I'm not going to spend time proving it again, since it's exactly the same proof as we had many times. Just a different type signature. And notice also f here is an arbitrary applicative functor. So these functions don't use the structure of f other than that it is applicative. So that's an example we have seen just before. We implemented a traverse function for this type constructor by applying the zip function of f. Otherwise, we don't know what f is. We just use zip from it. And so we are generic in the functor f, as long as it's applicative. We don't look at the structure of f. We do look at the structure of L. So the traverse function depends on the structure of L, but it doesn't depend on the structure of f. It's generic in f. Future.sequence has this type signature. And that's an example of the sequence natural transformation. Note we cannot have the opposite transformation. I'll show the example for that. But, well, for a future and list, you could make an opposite transformation. You have a future of a list, and you produce a list of individual futures that are going to be all already copies of this future mapped to select one copy of the element. You can do that. It's kind of useless to transform in the opposite way. But what I will show on examples is that it's impossible to have this transformation in general for an arbitrary f. It's possible for future, maybe, but not for an arbitrary f. So examples of traversable functors. This example we have already seen. List is another example, sequence in general, and also finite trees of various shapes. They are also traversable. An example of a non-traversable functor is the reader monad, and also the lazy list or infinite product, or stream as it's sometimes called, lazy stream. So let's see why that is so. Let's implement the sequence for this type constructor first. So I'm going to define this type constructor for convenience, and the seek function, as I'm just going to define directly, is going to have this type signature. And that's just a zip applied twice, and then some reordering of the nested tuple that results from the zip. And we know this is associative because we assume that f is applicative. Now I'm using my own type class for f, which I called woozip for applicative, but you can also use cat's applicative. Just has a slightly different name for things, and it doesn't have the zip syntax, so I'd like to use the zip syntax. So I'm using my own type classes here, but it's equivalent to standard applicative type class. So the sequence function has this type signature. Just as we have seen in the case of filterables, monads, and applicatives, it's much easier to reason about this natural transformation rather than to reason about the lifting. It's also will be the case that laws are simpler to formulate. So that's why I will always define just the sequence function. I will not define the traverse function. The traverse is easily defined in terms of a sequence like this. And I'm therefore in this tutorial concentrating entirely on the sequence function. I'll never implement traverse directly to save time. So let's have another example, the either as a functor, either ZA, where Z is a constant type. Then the sequence must have this type signature. So it takes an either of Z f of A and puts f outside. So it pulls the functor f from the inside of our type into the outside. That's the type signature of sequence. So how do we implement that? Well, we need to match. So if it's a left, we have a z. We need to produce f of z. So the only way to do that is to use the pure method. Let me interchange the order of lines here. The left z does not have any f of a, and so in order to produce an f of something, we have to use the pure method from f. And then we apply that to the left of z, and then we get the right type. If we have a right of fa, then all we need to do is to put a right inside of f. So we just map that. We don't change the value of a, we just map it to wrap it into the right type constructor. So that's a very clearly simple implementation. So if we write this type signature using a short type notation, then maybe it's even easier to understand how the sequence function works. So if we have a z, then we just put z inside f using the pure. If you have f of a, and we just put a 0 plus a into f by mapping with the right type constructor, so that we don't change this value a. Let's see how to implement the sequence method for a tree type. So here's a simple binary tree. It has a value of type A at the leaf, and it has a branch of 2 trees. So how does sequence work on a tree? If we're in the leaf, when we just wrap in the leaf, like we did with this either. And if we're in the branch, then we apply the sequence method, which is the same sequence we're defining. It's a recursive function then. So we recursively apply the same sequence method to the left and to the right branches of the tree. And then we zip them together. So then zip is the operation in the f functor, applicative functor. And so we can use that to zip them together. We get an f of a pair of 2 trees, and then we wrap that pair as a branch under the map. So this map is under the tree, under the f functor. So f is an arbitrary applicative functor, and we're using its methods map and zip. And here we used its method pure. But other than that, we did not use any knowledge of f. So it is in this way that we are generic in the functor f. We are not using any knowledge about the structure of f, other than it has a map and zip and pure methods. Let us see examples of non-traversable functors. So here's an example. It's a reader monad with a type parameter e. It's non-polynomial, and so it will turn out that this is not traversable. So let's see why. Let's take some applicative functor f, specifically like option A. And let's find all implementations of this type signature, which is the type signature of sequence. Now, all implementations turn out to be just 1. And this implementation always returns none. So it always returns an empty option, ignoring its argument. So it is not a very interesting implementation. And we will see shortly that this would not satisfy laws of traversable functors. So this satisfies the type signature, but it does not satisfy the laws. We haven't yet seen the laws, but it is reasonable to see that this function completely ignores its argument, so it loses information. And a typical laws for a lifting would be identity and composition laws. Identity law would tell you that some lifting is identity, but if it's losing information, it cannot be identity. So it cannot preserve the data that you give it, because it will lose it. It will always return empty option. And so that's reasonable to expect that this is not a good implementation. And so there are no good implementations for this type signature. Let's take another example. And we'll see there's one implementation for this. So we can actually implement this type signature for this applicative functor. And this code is what you would expect. It's taking this function, so let's translate the type signature. This is e to the pair, and this is pair of e to a, e to a. Now, if you have an e to the pair, and you can produce a pair of e to a, e to a, that's very easy. You just duplicate your function. So we do have implementations for this, but we're supposed to produce an implementation of sequence that is generic in the functor f. So we cannot look at the structure of the functor f and have a different implementation for every f. It needs to be generic. And so because we cannot implement it for some f, we're stuck. This is not a traversable functor. Let's take another example where we have a pair. So the pair of some type in A, the polynomial functor. And let's take this as the applicative. And again, we find that there is an implementation. So that's fine. So this is actually traversable. Let's consider the infinite list. So the infinite list class needs to be defined because we cannot have recursive type as a type alias. We have to have a class. And it's a pair of a value of type A and a lazy evaluated tail, which is again an infinite list of type of values of type A. So let's define a sequence method. Well, we can actually define it. It's quite easy. You take the head of the list, you zip it with the recursive application of the same function sequence to the tail of the list, which will sequence or permute the order of functors. And then you wrap it into the infinite list again. So that's similar to our implementation for the sequence operation on a tuple, except that it's recursive. And it turns out this is infinite recursion. Let's check that even the simplest functor f, the identity functor, let's define it like this, put some type class instances for identity functor, which is trivial. Let's define an example value of an infinite list, which is defined like this. It's a recursive definition. We could do a lazy val instead of def, I believe, but it's just cleaner to do a def since it's a recursive function. And you see the tail of the list will return again the same list. So it's going to be an infinite list of 123 all the way to infinity. So if we use sequence on this value, then we get a Stack Overflow error, actually, because it's infinite recursion. So it's an infinite loop. There's no way to implement the traverse of an infinite list, because basically what we need is we need to sequence like this. We need to have a list of f values, so it's an infinite list. So it's an f of a, infinite list of f of a's, and that should be mapped into an f of infinite list of a's. Now, how can we do that? We need to pull f outside to the outside of the type, which means that we need to evaluate infinitely many of these f's in order to pull f outside. I mean, generically, that's what we need to do. We need to evaluate infinitely many elements of this infinite list in order to put f outside. It's impossible to just pull f outside magically, out of the infinitely many elements here. And so even when f is just an identity functor, this won't work. It's impossible to pull f outside. I mean, it would be possible for identity functor, of course, but we have to be generic in the functor f. We cannot use any methods on f other than zip and map. And so we don't know what f is. F could be something that needs to be evaluated in order to pull a out of it. And so because of that, it forces us to evaluate infinitely many elements before we even get a single value of this type. And so that will never end. So that's impossible. So for this reason, the infinite list is not traversable. And finally, I mentioned that the opposite type signature is unworkable. So why? Let's make an example, a calculation. So let's say L is an ether, which we know is traversable. F is this reader monad, which we know is applicative. So let's find all implementations of this type signature, and we find there are none. There is no implementation of this type signature. The reason is that this type signature would have to map this function into this data. But that is impossible. You cannot extract a z out of this, so you could not possibly return a z, because you need an integer. So which integer are you going to give? Imagine that this integer is a different data type. You don't have values of it necessarily. I mean, for integer, you could put 0 in that integer, sure. But that would not be reasonable for other types. So you cannot possibly pull z out of this, because there aren't any special values of this type. And you can also not get this function, because you only have this function, and this function could sometimes fail to return an a. It could sometimes return a z. So for some integers, it could return a z, and you don't know in advance for which integers it will return a z, and for which it will return an a. Until you run this function on every possible integer, you won't know that. And so that's impossible to know, and so you can't split this into a z and into a. You couldn't either split it into two functions, int to z and int to a, for the same reason. In order to split it, you'd have to run this function on every possible integer and see what the results are. So that's unworkable. And so that's why you don't have, that's an informal reason why you don't have any implementations of this type. And a final comment is that there are several ways of implementing the sequence, usually. So let's consider this type again. We have seen we can implement the sequence by applying zip 2 times. And here's another implementation. We can arbitrarily select a different order. So instead of zipping 1, 2, 3, we zip 2, 1, sorry, this is a mistake, 2, 3, say 1. And that's valid. So the type is right, and the laws will hold as well. We'll see why. So that shows you that there's more than one way of implementing the traverse or the sequence function, which is equivalent, for a given type constructor L. Different valid ways of doing it. So let's find out if other polynomial functors are traversable. Now, one of the central results here is that all polynomial functors are traversable. We will show this quite rigorously later. So for now, let's see how we can implement the traverse or the sequence function for an arbitrary polynomial functor. So we have done it so far for this, and we have also done it for either, which is a simple polynomial functor. And a general polynomial functor would have this form. It's got a polynomial in A with some constant coefficients, which I here denoted as z, y, q, p. So we have seen how to implement for monomial. So let's first consider monomial like this. So one part of this polynomial. Then we can apply zip to these. So first we look at LFB. So LFB has this type. So we can apply zip to these. We get this. And then we can lift the z into the functor f by just this standard functor map. This function is always possible for any functor f. Alternatively, we can do f pure of this z, and then this will become fz, and then we can zip it together with all others. But the result will be exactly the same as using this function because of the law of identity for applicatives. So the result is going to be this, and then that's the sequence method for a single monomial. And then for each monomial you do this, and you have a disjunction of different results of type f of a monomial, and then we lift it to f of the disjunction like we did in the either implementation. So we have seen therefore that we can perform the traversal equivalently the sequence operation on monomials, and we can also perform them on disjunctions, and therefore we can perform them on arbitrary disjunctions on monomials, and that's arbitrary polynomial functor. Also note we could apply zip here in different orders. We could first zip this and then put z on the right. We could change orders in different ways. And so the traversal order could be application specific. It could be necessary to adjust it for a certain application. You can always implement in some order or automatically say, but it may not be necessarily correct for your application. And also we have seen that non-polynomial functors, at least some of them, are not traversable. So this is not traversable because we cannot have a reasonable implementation of this that does not lose information. And there's this paper that I'm referencing here. It's a complicated paper, very theoretical, but it has a proof that only polynomial functors are traversable, and also that they must be finite. So infinite lists do not fit the conditions of their theorem. Only finite containers. Polynomial functors are essentially containers with data. They can have different shape. They can have many items of data, or few, or none. It could be a disjunction of different shapes. And they also can have extra data of some constant type, in addition to data of the type A. But those are the containers that are traversable, and no other containers are traversable. So if you have a lazy infinite stream, that's not traversable. They have to be finite, and they have to be polynomial. So that is proved in this paper in a complicated way. So I'm not going to try to understand how they did it. I believe that this is so because I have examples that even the simplest non-polynomial functor can't have a reasonable implementation of sequence. So even though all polynomial functors are traversable, they are usually traversable in several different ways. And so it's useful to have a type class to declare a specific instance of a type class expressing a specific order of traversal. So this order of zipping that we can choose here corresponds to ordering of traversal, in a sense. We will see that when we look at specific examples of traversing. But now let's take a look at the laws, because we have been talking about the laws so far, and we need to see in more detail how they work. So I prefer to look at this type signature of traverse and to derive laws using the lifting intuition. So it's a lifting of sorts, and every time we had liftings so far, we had laws of identity and composition. In other words, there was some kind of identity here and some kind of composition of these, and this has to translate into identity here and composition of these. I will mention that there is this paper which is arguing what laws traversals must have from a different perspective, not as formally as I have argued just now, because my argument is completely formal. Traverse looks like a lifting, therefore it should have laws like the laws we had before for other liftings. It's purely a formal argument saying that the form of this function is similar, therefore it should have similar laws. But this argument doesn't look at what traverse actually does. Well, what it does is that it evaluates some function on each element. This function produces some effect, maybe. This f is an applicative functor, which could be a monad, or it could be non-monad, but it encapsulates some kind of effect, some kind of computational context or a result other than b. And all these contexts need to be somehow put together and be outside of the LB. So we need to reconstruct our container L inside the larger effect described by F. So we need to somehow combine all these effects for individual values of A into one big effect, which would be outside, and then we have to combine all the values of B, have to somehow pull them out, combine them again into the same shape as the container L, inside the F. So all that needs to be done by the traversal function. And the authors of that paper argued that the traversal, first of all, should visit each element of the container exactly once. It should evaluate each effect exactly once, and then combine these effects into a larger effect. And using this intuition, they formulate some laws that seem to fit this description in some way. Well, they didn't actually derive these laws from these requirements, but they showed examples where these requirements are violated, and they showed that these examples also violate the laws. So this is a little not very convincing to me that these laws are correct, and therefore I prefer the more formal approach, because I have more assurance that if I find some reasonable identity and composition laws, that's a correct set of laws. So far, in every example we have seen, with functors, with contrafunctors, filterable, applicative, and monad, every single example had a function with a type signature like this, which was like a lifting in my terminology. And in every single example, there were identity law and composition law. And these laws were equivalent to all the other set of laws that were derived from intuition. And these laws also corresponded to some category laws. Now, in this example, I don't know how to formulate this in terms of a category in a way that would be simple enough. So I'm satisfied that I find a law that looks like identity law and a law that looks like a composition law, even though I'm not satisfied that I can find an easy enough category to reason about so that it's useful. So I'm not going to talk about a category in this chapter. I'm not going to describe this as a lifting from one category to another, because I don't know if that's really very useful. And I don't know a good formulation of that. So let's look for these laws. So identity law is that we map some special function here that is identity in some sense into a function here that plays the role of identity. Now, the type signatures are not A to A, they are A to F of B. So what could be playing the role of identity here? Well, the pure method, obviously. And F has that method by assumption. So the identity law is that if we put a pure method here, then it should be lifted to this, which is again a pure method, except it's applied to a different type parameter. Now, another way of formulating identity is to say that if F is the identity functor, so then there's no F here, just B, then identity function here is ordinary, A to A, and that should be lifted to identity LA to LA. So F is just identity functor, and then this identity should be lifted to this. So that is another way of formulating an identity law. Let's find out. Now, to compose, what would be the composition law? If we have two of these functions, like F and G, then we can compose them using fmap. But the result would be this, because the fg would be nested now. We take fb, we map g over it, and we get f of g of c. Now, if f and g are applicative, then the composition f of g is also applicative. We know that from the properties of applicatives. And so it is again a function of the same type, except that it has a different functor instead of f. So f functor, g functor, and the composition of such functions is going to be of this kind, which is kind of complicated. It changes the functor each time. So what should be on the right-hand side? Well, it should be a composition of these traversals. Now, the composition of traversals obviously works in the same way. So you have LA to FLB, and then FLB to FGLC. And so that is your final traversal, and that should be equal to applying the traversal right away with this functor as applicative functor. In other words, applying traversal to this. If that is true, then traversal of composition is equal to composition of traversals. So that's with a little twisting, where we keep using fmap in order to get composition, and we keep pulling all the functors f and g, all the applicatives, we keep pulling them outside. With these twists, it looks like just a composition law. Traversal of composition of f and g with some twisting is equal to the composition of the two traversals with f and with g, again with some twisting. So these are the laws we're going to examine, and it will turn out these are exactly the same laws as this paper proposes. When I first looked at this, it looks like we have two identity laws. Are they really independent? No, they aren't. We'll see that. But that's a question we need to answer. Also, laws for sequence are probably going to be simpler, because in our experience so far, always we found that the laws became simpler if we consider the natural transformation instead of a lifting. So let's find those laws for the sequence. And finally, with the laws in hand, we can try to answer the question of which functors satisfy these laws. We have found examples where we can implement the type signatures, but are the laws respected by those examples or not? So that's the questions that we have after this point. So let's look at the first identity law. So the traverse of pure needs to be pure. So that's the first law. Let's look at the type diagram for this. So we start from LA. We map it with pure, or we map it with traverse of pure, and it should be the same value of type f of LA. So that's the first law. Now the second identity law looks like this, and it's clearly a consequence of the first identity law if we just put f to be the identity functor. And the first law should hold for every applicative functor. So we really just need this one law. And the second one is a consequence. So let's forget it. So we have the identity law, which is this. And we have the composition law, which we can write like this in the short notation. So for any function of this type, and the function g of this type, and for any applicative functors f and g, we have this law. So the composition of f and g is twisted in the sense that g must be lifted by functor f. So this is our twist on the composition. Other than that, composition of two traversals is equal to traverse of composition. Here we twist, and here we twist. Let's look at the type diagram. We start again with LA. First we traverse with function f, and we get FLB. Then we want to traverse with G, but G works on B, so we have to traverse just on this LB, and F needs to stay outside. Therefore we use fmap of F, and we traverse inside of F using the traverse of G, which is giving us this value, FGLC. Or we could directly traverse on the function h with respect to the functor f of g, which is a functor composition. So the functor h could be defined like this as a functor composition of f and g, and we know it's applicative. So we could just directly traverse with respect to h. So this could be traversal with respect to h of a function h of this type. And this function is defined like that. So this is the law that we demand now that should hold. Let's derive the corresponding laws for sequence. To do that, we just express traverse like this through sequence and substitute that into the laws of traverse. So let's look at identity law. Traverse of pure equals pure. So traverse of pure equals this, and that should equal pure. So that's the law of identity for pure. So pure lifted to L and then sequenced should be the same as pure applied to the type parameter LA. I should also mention naturality law. Now, that's always the case for all of our examples so far, such as filterable, monad, and applicative, that all these natural transformations, as well as the liftings, they have naturality laws. For each type parameter that they have, there's one naturality law, which expresses the fact that the code implementing that function does not use any information about the type. It's completely generic in that type. And so you can map this type to another type before the transformation or after the transformation, and the results are going to be the same. So here's what the naturality law looks like for the sequence. Now, sequence has a more complicated type signature, and its type parameter A is all the way inside. Therefore, in order to transform this A to some B, we need to have a double fmap. So let's say there's some function g that transforms A to B. In order to transform this A, or transform that A, we need to lift this g twice, and that's how I would write it down. So first we can sequence this LFA to FLA, and then we can lift g twice in this order. Or we can first lift g twice in this order, so that instead of LFA we get LFB, and then we sequence on that. So that should be the same function. That's a naturality law. Yeah. And the code for sequence will automatically respect that law if it is a code that is generic in its type parameter A, if we never use any information about the type of A. So usually naturality laws are satisfied automatically by generic code, and so it's not important to check them, but it's important to check the other laws. So now let's look at the composition law. We need a bit more work about it. The traversal of f followed by the traversal of g lifted. So let's substitute the definition of traversal, and then we get this formula. Now we can decompose the lifting of composition by the functor law, so we can get like this. Now, the naturality law means we can interchange this, and we get that. And finally, the right-hand side is written like that, so again, we can do that because of the functor law. So, in other words, the composition law for traverse says that this is equal to this. They have a common prefix that we can omit because these are arbitrary functions f and g for which this must hold. And so it's sufficient that these things are equal. So that's the law for sequence, much simpler. And here's the type diagram, because the types here are actually complicated. So we start with an L of f, g, c. C is some type parameter. I could use A here, but I just had C. Now first we sequence with respect to f, and then we just pull f out, and we get FLGC. Then we sequence with respect to g, but we lift it to be operating inside of f. So that means we interchange this L and this G. The result is FGLC. Alternatively, we could sequence with respect to the functor f of g. This is maybe not a very nice notation, not very consistent, but this is the composition of functors f and g. So it's the h that I mentioned here. I should probably, for clarity, I should use h instead of fg. And so if we sequence with respect to fg, that means we pull out fg at the same time to the outside, and we get fg of lc. So the result of these two computations must be the same. Having formulated the laws, we now can look at constructions, and we can check that the laws hold. We can also check whether some functors can be traversable when they are polynomial, or when they're recursive, or when they're not polynomial. So we have so far seen some examples, but now let's be more systematic about it. Here are the constructions that I found for traversable functors. And I will go through each of them one by one now. Now, before I do that, let me explain what is a bitraversable and bifunctor. So a bifunctor is a type constructor with two type parameters, which is a functor in both of them. So it has a map with respect to each of them separately. And it also has a map with respect to both of them at once, of course, because you can transform A to some C and B to some D separately or at the same time if you wish. It doesn't matter. So that's a bifunctor. And bifunctors are bitraversable in the following sense. They have this natural transformation where we have an f wrapping each of the type parameters of S. And this f can be pulled out by this sequence, bi-sequence, natural transformation. And it should be natural both in A and B separately. So that's the assumption. And so you see this A and B remains, and we have pulled f out to the outside. So if such a transformation exists, which is natural in both A and B, and it has the same laws, the laws of identity, and the laws of composition. Now the law of identity is this. And it needs to be adapted, obviously, to this bi-seq, so that you have pure here and pure here. And the law of composition obviously needs to be adapted as well, because you have FGA, FGB, and so on. But other than that, it's a direct generalization. So analogous laws must hold. So let me now begin by deriving the laws that must hold for these constructions, or rather deriving the fact that the laws hold for these constructions. The first construction is constant functor and identity functor. So both of them are traversable. To define that, we need to define the sequence method and to show that the laws hold for it. And that's very simple. So for convenience, I'm just going to put the type parameter up front. The constant functor is a functor that doesn't depend on its type parameter. So L of f of a is the same as fL of a, the same as this constant type z. And f of LA is f of z. So sequence is this type signature. And clearly this is f dot pure. It's just a pure of f functor. We can't in any other way produce a type signature like this that is generic in f. We are not allowed to know what f is, except that it has a pure method, zip and map. So let's just define that as a pure. Let's check the laws. So the identity law is that f map of pure followed by sequence must be equal to f dot pure. Now I'm putting here this underscore L notation for clarity. I could have said, for example, instead of f dot pure, I could have said pure underscore f. What I mean by this is that it's the method that is defined for the type constructor f. So this method is not generic in f. It is defined for each f separately in the type class instance. Similarly, fmap is not generic in L. It's defined for each L separately. So I could have written like this as well. It's not Scala notation necessarily, but it will do for now, just for clarity to remind myself where these methods come from. Now sequence is defined for L. So here I could write it like this. To remind myself that the sequence is defined separately for each L, but it is generic in F, so I could write it like that. So sequence has F as a type parameter, but L as a type constructor or functor for which it is defined in the type class. Now, so let's see if we can verify this law. Fmap is identity for the constant functor. So this is identity. So this is just f pure. Sequence is fmap of f pure is identity function. Fmap does not transform anything because there is nothing to transform. We only have this z. It cannot transform. So this is just identity function. We can cross it out. And then we have the law that sequence equals pure, but sequence equals pure by definition. So the law is satisfied. Let's consider now the composition law, which is the composition of sequence of f and the lifted sequence of g. So now I'm using this notation with more sense, and here I didn't have to say it's sequence L of f. I could just say sequence. But here it is important now to say for which type parameter, because the functor is a type parameter in the sequence function. So we have the sequence applied with respect to applicative functor f, and this with respect to g. And fg is the functor which is the composition of f and g. We just denote it like that for brevity. So this is the law. Now, sequence is defined as pure. Fmap is defined with respect to f. So this is fmap f, not fmap l. Fmap l was identity, but fmap f is not. And we actually don't know what it does, because f is an arbitrary applicative functor. So we need to keep it symbolic. So we have f.pure, which is this sequence, and then, because the Scala operation and then corresponds to my composition symbol. And then we have fmap f of g pure, because this is the pure in g. And that should be equal to fg pure. But actually, what is the definition of pure for composition of functors? That's exactly this. It's a pure of f followed by lifted pure of g. So it's a definition of what pure is for the functor fg. And so therefore the law holds. Now consider the identity functor. Now the identity functor is like this, or sometimes it can be denoted by id with a capital I. So this is identity functor. I believe the CATS library does this. Maybe not. Maybe Scala Z. So how do we define a sequence for it? Well, this is just an identity function because it doesn't do anything, because we have f of a goes to f of a, because it is just a wrapping, it doesn't do anything. So this is identity function. We could even write this sequence function differently, like this. In order to underscore that fact that it's just identity function. Now, let's check the laws. The identity law, which is this. Now, if fmap is the identity function, sequence is identity function. Now, fmap L is just this. So fmap L is the identity function of its argument, because of this identity functor. And so this is equal to f.pure. So this is f.pure followed by identity. And that should be equal to f.pure. That's clearly so. Composition. Is that we have a sequence followed by fmap of sequence. Now, sequence of anything is identity. So it's just composing one identity and fmap of another identity. But we know that lifting fmap of identity is again identity. So this is just about composing one identity or another. that's always going to be identity. So that is also identity by definition. And so this law holds. Let's move on to the next construction, which is the product. For any traversable functors g and h, their product is traversable. Now I'm going to introduce my own type class for traversable, just for convenience. But actually, the cats library has a traverse type class. But I just want to show that this is easy. And I prefer to define seek, and they prefer to define traverse in their type class. So that's why I have my own type class, but basically this is a very simple type class that has just one method. And this method is LFA to FLA. And traverse is defined through that method. Now this red is a problem with IntelliJ, and the Scala plugin cannot resolve the types. It compiles, this entire code compiles and works. Also, we have a convenience method to get the traverse instance, this trav, and the syntax to use seek as a method rather than as a function. And that's all this code is just convenience for me. So let me then show how I can define an instance of trav, of this traversable type class, for this type constructor, which is a product of L1 and L2. Given that both L1 and L2 are traversable functors. So first I implement the functor instance. Well, that is standard. It's just I map this and I map that. Just the functor instance for product. And then I implement the traverse instance using seek. So what am I supposed to do? I have this L1 FA times L2 FA, and I need to give f of L1A times L2A. So first I can zip these. First I can sequence each of these separately because L1 is traversable and L2 is traversable by assumption. So I sequence separately both of them. Then I can zip the results and I get what I need. So that's my idea about how to implement. So I just say sequence the first one, sequence the second one, and zip. Now I could also write the code like this, I believe. But then IntelliJ doesn't understand where these things are coming from. But the code actually still compiles if I do that. So this is just much more verbose. It's telling me where the sequence comes from which functor. And in principle, I expect Scala to be able to derive this automatically, and it can. This is much simpler to write, but IntelliJ doesn't like it. So let's check the laws here. So there is the identity law, which is that we can map the pure and apply seek, and that's the same as the pure. So how do we verify this law? Well, we substitute the code of fmap, which is up here. And we apply both sides of this law to some arbitrary value of this type, L1, L2. So we do that looking at the laws. Actually, we have to start from LA, and the law will give me this. So the value on which I apply both sides of the law must be of type LA. So that's why and LA is a pair of L1A, L2A. So then that's why I take some arbitrary pair and I apply the law to it. So the left-hand side, first I apply this, and that's going to be that, because the fmap, this is L1 and this is L2. And then we apply the seek function to this. Now the code of seek is, I'm going to write it like this in a shorter form. And the result will be that I have this seek zip this seek. Now we need to assume, obviously, that the law already holds for L1 and L2 separately. And therefore, for example, we have this, which is the formulation of the law for L1. And so we can substitute that in here. And then we get that. Now, because of the identity law of applicative, the zipping of two pairs is a pair of the pair. So this equals the f pair of the pair. And that's exactly the same as applying f pair, which is on the right hand side, directly to the pair. So we have verified the identity law. Let's verify the composition law. This is how we could write it. I have written out sequence seek of L everywhere, just for clarity. So in my notation, that means the sequence method defined for the type constructor L applied with respect to the type parameter f. So now let's apply again both sides of this law to some suitable value. Let's see what type that value should have. It should have the type LFGC. That's the initial point on the type diagram. So let's have an arbitrary value of type LFGC. So instead of C, I use A here. So LFGA, an arbitrary value of that is a pair of L1 FGA, L2 FGA. And applying the code for seek to this, we get L1 FGA seek with respect to f, zip f L2 FGA seek with respect to f. So that's applying just the first step according to the type diagram. That would lead us in here, which is f of LGA, f of L1 GA, L2 GA. So now we apply fmap f of this to that. Now, what is fmap f of seek g? Now, seek g is with respect to L. With respect to g of L. So it acts on some value of this type, and it will give this according to the definition. But we need to lift this function with fmap f. The difficulty here is that f is an arbitrary functor. We don't know what fmap f does. We don't have code for it. We need to keep it symbolic. So clearly we need to use a definition of zip fg somehow to find out what fmap f will do. So the definition of zip of fg is this. There's some fgx and fgy. We zip them in the functor fg. So fgx is of type f of g of x. fgy is of type f of g of y. The definition of the zip for the composition is one of the constructions for applicative. It's a zip in the f functor followed by fmap f of zip in the g functor. Is this what we have in our formula? Well, not quite, because we have not just something zip f something, after which we do fmap f, but we have these things transformed with seek. So let's transform using some functions. So let's use a naturality of zip so that we can transform like this. So we transform under the functor f, and so the result is the same as if we transformed fgx and fgy and then zipped them. So that's a naturality. You can transform first and then zip, or you can first zip and then transform. That's up to us. So finally, if we use this formula, we can see that fmap f of seek L of g is like this. So it's the fmap f of this. So this is seek L of g, because seek L of g gives us this kind of expression, which is similar to this. P of gx being sequence of this, zip g, and Q of gy is sequence of this. And then we apply this to those things. And so the result is that fmap of seek L applied to that is like that. It's seek f map seek g, and then seek f map seek g. So that's what we find if we apply naturality of z. So that's the left-hand side of the composition law, and the right-hand side is that. So these must be equal. Now, the definition of seek fg is the code of seek that is just applied to this type parameter fg instead of the f. So the same code. And it would have been the same code if we could have this equal to that. Now, these are seeks with respect to functor L1. So these are defined for L1, and these are defined for L2. Now, we assume that for L1 and L2, the composition law already holds. So that means, for example, this. So this is the composition law for L1, and similarly for L2. So therefore, this is the same as this, and that is the same as that. And so the composition law holds for L. The third construction is the disjunction. So for any traversable functors G and H, the disjunction is again a traversable functor. So we have seen an example of implementing this in either and in polynomial functors, but this is a general construction, so let's see how to implement it. Again, we assume that functors L1 and L2 are traversable, and we define L as the disjunction of L1 and L2. Standard functor instance per disjunction. So now let's implement the functor instance, traversable instance for the disjunction. So here's how it will work. We have this, so we apply sequence to each of these separately. We get this disjunction. And finally, we, depending on which one we have, we lift it into the f of disjunction using just constructors of the disjunction, left or right. So that's how it works. First we do a sequence on each of them. So if we are on the left, then we sequence it, we get this, and then we map it with left apply, which means that we put a left on top of this. And left is just a wrapper in the disjunction, so it doesn't change the value. And the same we do for the red. Now the redness here is again due to limitations of IntelliJ. It's unable to infer types correctly, but this code runs, it compiles and runs. So let's check the laws. Identity law. We do the same thing as before. We just substitute the code of fmap in here, and then we apply to some LA. We know that both sides of the identity law apply to an arbitrary element of this type. Now, since the code is symmetric with respect to L1 or L2, it's sufficient to apply this to some left of L1A and check the law for that. So if we apply it to a left and we are in this case, then we have a left applied to this, which is well, we are actually in this case, so we're looking at fmap L first. So we are going to lift like this. Now, notice we can't really simplify this because these are map and pure methods of functors that we don't know. These are L1 functor and F applicative functor, so we don't really know what these methods do. We cannot substitute any more code. So that's our symbolic computation right now. We apply seek to this. Now we're in the left. So we apply seek to this, which is, I'm going to denote it as seek L1 to that. And followed by map of left apply. Now, nothing more to simplify unless we use the fact that L1 already has this law. And so this law for L1 looks like this. Therefore, we can simplify here, substitute that, and we get F pure of L1A map left apply, which by naturality of pure would be F pure of left of L1A. And that's exactly what the right-hand side would do when applied to left of L1A. So the identity law holds. Let's consider the composition law. The composition law needs to be applied to a value of this type. And again, it's sufficient to consider the left and apply to that. So first we apply the seek, and that gives us this. Now we apply fmapf to that, and we notice we have fmapf, which is this one, and another fmapf, so we can combine them. And the result is that we have this, to which we apply map with respect to f of this kind of function. So we first do a left apply to that, and then we further apply this function. So now this is not quite Scala code, because I have this map underscore f for convenience and clarity. So that's just keep in mind. I'm not actually using pure Scala code here, but I could. It's just that the types would be less clear. So now, what does this do? Now, this seek g, not seek g, has to act on the left. And we need to substitute the code of seek. When acting on the left, it gives us this expression, by definition of our seek up here. So let's substitute into this, and we get then this expression. So now we can use the composition law that by assumption already holds for L1. So then we have this law for L1, which we can rewrite like this. Now, this law is not quite giving us the expression that we want, which is this expression, because we have this function here, but here we have another map. So we have another left apply to map. And also on the right-hand side of the law, we have another left apply. So in order to put another map inside the seek, we use a naturality of seek. We add this on the right-hand side, which gives us this seek. So seek is natural, so we can apply seek to a transformed argument, or we can apply transformation to the result of seek. And so then, if we define what map fg is, that is fmap of fmap, and we put that onto the left-hand side, so then we have seek L1 of this, map f of this, map f of that. Now we can combine the map f's, this one with this one, and then we have a single map f with a bigger function. But that's exactly what we had for the left-hand side computed before. And so therefore the right-hand side corresponds is equal to the left-hand side as code. So the code is equal. And the same would be if we replaced L1 and L2. So this shows that laws hold for disjunction. Now let's consider this construction 4, which is a recursive functor, defined as LA equals some S of A and LA. So this S is an arbitrary bifunctor. So this could be any type function of 2 type parameters. And this equation, this is a type equation that defines the type LA recursively. So examples of this are lists and trees. Different functors S can encode very easily different kinds of lists and trees. Now, this also describes infinite lists and infinite data structures. And we have seen an example where the infinite data structure does not actually work. You can implement the function, but the recursive calls never stop. So that's the problem. The laws will appear to hold in our proof, but actually it will not work in practice. So I will comment on this when I use the recursive assumption in the proof. So let's see how it works. So I introduce the bifunctor as a type parameter up front so that I don't worry about it so much. It's easier in Scala to do this. Now I cannot just introduce a type like I did here, because recursive type aliases are not allowed in Scala. So I need to introduce a class. So let's that actually makes the code a little clunkier, because now I need a name for the data value inside, and I need to wrap and unwrap. But that's a small inconvenience. So the class contains a value of type S of A and of the same L of A. So this is a type function that I'm considering as a parameter. And now I can implement a functor instance for this. Now this obviously is going to be recursive. So in order to map this LA to LB, I map A to B here. And I need to map this LA to LB recursively by using the same map. So I need to do this under S. So I need to map at the same time A to B and LA to LB under the type constructor S. So that's bimap. So I'm mapping the two type parameters of S at the same time. And then bimap is a method that takes two functions with two type parameters. So it goes A to C. And in this case, we have the bifunctor with type parameters A and L of A. And so it takes two functions, A to C and L of A to D. It gives you S of C, D. So this is combining map with respect to the first parameter and map with respect to the second parameter in a single call, which is completely equivalent to doing the first type parameter with a map and then the second type parameter with another map. But it's just easier to do it with one method rather than two. And this is the recursive call to the same function. So this is how we do it, the functor instance. Now let's look at the traverse instance. How would that work? So L of A is the same, is recursively defined as S of A and L of A. So now we need to transform this into this if we want to implement seek. How do we do that? Well, we can obviously seek here recursively. So the second argument of S is a recursive instance of the same type. And so we can assume that for that recursive instance, we already have the implementation. So that would be the recursive call to the same function. So that would be transformed into FLA. So now we have, so we just do a bimap where the first one doesn't do anything, it's identity. And the second function is a sequence, recursively calling the same. And now we do a bitraverse, or bisequence, actually bisequence, which is, as I indicated before, it's transforming SFAFB into FSAB, pulling out the F at the same time out of both type parameters to the outside. So we use that and transform S of FA FLA into F of S of A LA. So this is exactly what we need. So in other words, seek is just a composition of bimap and biseek on that bifunctor. Now I can use cat's library. It has bifunctors, bitraversable, and it has this bisequence. And so I'm using bifunctor and bitraverse, which is the cat's library type classes. Just I could have defined them just as easily as the trav type class. And the redness again is some problem with types, although I indicated all types explicitly, but still it doesn't like it. So therefore the seek is just bimap with identity and seek, which is a recursive call, followed by the bisequence call on the bifunctor. So that's exactly what we plan to do. First we bimap so that we seek under S with respect to the second type parameter, and then we do bisequence on S. So that works, and let's check the laws. So the identity law, we need to substitute the code. Now for clarity, I still write fmap L here and so on. But it is easier now to distinguish sequence with respect to L and S because S is a bifunctor, so it has biseek and bimap, and L has seek. So I'm not going to write seek L. I could have done it like this, but I'm not going to write it for clarity, for brevity rather. So, okay, substitute the code of fmap L, and that gives us this code, which we defined here, the map instance, the functor instance for L, which maps using bimap on the F and the recursive on the second. So let's write it down. So this is a bimap of this function and the recursive fmap L as a second argument of bimap. So the same function as we're defining here is here. So now we need to apply seek to this. The result is this followed by bimap, actually followed by bisequence. So I remind myself, what is my definition of sequence for L? It's just take the S out of the case class, which I'm not going to write here because it's just wrapping and unwrapping. I'm going to pretend that this case class is just a type. So first it's a bimap with identity and seek, and then it's a biseek on the result. I'm going to ignore this because this is just wrapping. Right, so seek in L is bimap followed by biseek. This is seek L. I'm not going to write L. So we have this expression. Now we can combine the bimaps just like we can combine maps because they're bifunctors. It's just first we have a map in the first type parameter, so we combine these two, which gives us this, and then we have a map in the second type parameter which combines these two, and that gives us that. So fmap L and then seek is the same law that we're trying to prove. that fmap L of pure and then seek is f pure. So it's a recursive invocation of the same law that we're trying to prove in the second function on bimap. So we can use inductive assumption that we already proved that by recursion. And therefore we just substitute into this expression, we substitute f pure instead of this, because that's the law. So then we get bimap of pure by seek. And the identity law for S means that S bimap pure by seek is the same as S is just pure. And so that's, we assume, holds for S because it's a bitraversable bifunctor. And so this becomes the right-hand side of the identity law. And that's the proof of the identity law. So now a remark about using the recursive calls, and it is that inductive assumptions correspond to recursive calls in code. So in mathematics, the inductive assumption is that on the previous step, things were already proved. In code, it means that we are going to call the same function recursively, assuming that it will return the correct results. Then our step also returns the correct results. But that assumes that the recursive call terminates and actually returns the results. And we have seen in the example that on the infinite list, it does not return. It has an infinite loop. And so that's where it is going to break. So actually, the inductive assumption can be used as long as all these functions actually terminate their evaluation and return their results. And if so, then it's all fine. But so at this level, we will not see any problem with infinite lists. We are using the inductive assumption and everything appears to be correct. However, we have not established that these functions will actually return at all. And for the infinite list, they don't. And so for some functors defined using this construction, using some bifunctor S, some functors will have infinite loops and others won't. So that is a separate thing we need to establish in order to check that they are actually traversable. This is usually not a problem for functors because this map is going to be called maybe later, and this is a lazy call, and so there is no infinite loop, but we have seen we do a bimap and then we do a by sequence, and so that call will evaluate everything, and that will break for the infinite list. Now, all I'm saying is that this proof of laws, and the same will apply to the proof of the composition law that I'm going to talk about shortly, this proof is only as good as the fact that all the functions return. And if you have an infinite loop in one of the implementations, then this proof will break because the inductive assumption cannot be used. Because the use of inductive assumptions is translated into recursive calls in the code, and if those calls never terminate, then you can't call them. So I'm not going to present an analysis here as to what possible functors S are admissible, because I don't know how to do that analysis in general. So, and that's a much more difficult topic of recursive types. What are the recursive types for which certain methods would terminate? And that's for another chapter. So for now, we will assume that we check separately that all the methods will terminate, and if that is so, then this proof is correct. We are allowed to use inductive assumptions. Let's look at the composition law. So this is the composition law. And the law is an equation, both sides of which need to be applied to an arbitrary value of this type. Let's check. So LFGC. So use A instead of C. I'll probably make it in the slides that this is A and not C, because I'm using A in the code for consistency. So S of FGA, LFGA, so that's LFGA. So let's apply both sides of this law to some value of this type. And then we get first a sequence, which is bimap of identity and sequence, followed by biseq. And then we do a map of seq, which is a function that takes this and does a bimap and a biseq, but now with respect to G. So I'm just writing it out, what the code is for seq. And this should be equal to bimap followed by biseq, but with respect to FG. So that's our law. Let's check that this holds. And we certainly assume that it already holds for the S bifunctor, which means that this equation holds. And biseq map is biseq. Now this is just the law. This twisted composition of seq and seq is seq of FG. So how do we use this in order to prove this? Now, clearly, to use this, we need a value of this type, which is not the same as what we have here. Now, this is S FGX FGY, so it's very homogeneous. It must be the same functors, FG, and we don't have the same functors here. We have FG and then LFG, so this L is outside. If L were inside of all of this here, then we could just say this is Y. This is L of A is Y, A is X, and then we are of this shape. So that means we need to permute L over there. So in order to do this, we need to sequence this with respect to FG, and then L will get inside. But we need to use the sequence inside the type constructor S, which requires a bimap. Now, this is going to be a bimap with respect to the second type parameter of S, which is the recursive invocation. And so that bimap and sequence is a recursive call to sequence. Therefore, we can use the law of composition for that, as if it's already proved. And we will do that. So here's what we do. So in this law that we are going to use now, we're substituting this value, SFGXY, which is defined like a bimap, where we sequence with respect to L and respect to F and then G. And then that's of the right shape with X equal to A and Y equal to L of A. So that's what we wanted. And the result is this expression, which is a bimap followed by biseq followed by map. Now, we can certainly use Naturality and exchange map sorry, no. Here we're having biseq f map biseq g. That's what we're using here. It's a biseq fg. That's the law. We're just writing out the law. We're substituting sfgxy into both sides of the law. So this is here, and this is here. So this holds. This is an equation that holds. So now, by inductive assumption, the composition law for seq L already holds when we use it here. And so therefore we can rewrite this right-hand side like this. This is just seq L of fg. Now this right-hand side is the same as the equation that we need to check, which I noted as a star. I just labeled that equation by star for convenience. So the right-hand side of that equation is now the same as this. Therefore, it's also equal to that. So it remains to show that the left-hand side, is equal to the left-hand side of star. Let's write it down. So maybe like this. Yeah, it's maybe easier to compare. So by map, now we have this instead of that. And we have a biseq, and we have a map of biseq instead of this. Now, if we look carefully, we have a map f of biseq, and here we have a map f of something that's followed by biseq. So that can be pulled out with a map f and omitted. So this is a trailing map f of biseq of g in both of these sides we just omitted. We get this. So now the problem that they're not equal because we have a different order of biseq and map. So we have a biseq followed by map here, and here we have a map followed by biseq. When we need to interchange a map and a natural transformation, that's naturality law. And it's the same way for bifunctors. Just biseq and bimap can be interchanged. Let's write down the naturality law for clarity. It looks like this. So we have a biseq followed by map f of bimap of something, and then we have a bimap of map f of that function, that other function. So we have two functions because bimap takes two functions. Both of them need to be mapped, and then we have biseq at the end. So we have interchanged the order of biseq and map f. So if we use this law in this equation, then we get that the first line is equal to, we can interchange biseq and bimap, and we get biseq at the end. So now we have bimap followed by bimap followed by biseq. Bimap can be combined, and then we have this bimap followed by biseq. And this is exactly the left-hand side, which is this. Omitted biseq of g. Sorry, this one, actually. So this concludes the proof of the composition law, and therefore we find that this construction is valid. Now, the question is, which bifunctors are bitraversable? And the answer is the same. All polynomial bifunctors are bitraversable. Now, we see without recursion, these constructions 1 to 3 are constructions that allow us to get any polynomial functor with arbitrary types in it. It doesn't have to be monoid. like in applicative, can be any constant type, any polynomial functor. These constructions cover all these cases. Now, construction 2 even has two different implementations. We can zip in one order or in the opposite order. It still will work. And therefore, all polynomial functors are traversable. Now, exactly the same constructions work for bitraversable. Constant and A and B are bitraversable in the same way as constant and identity functor are traversable. And products and disjunctions are bitraversable. And so all bitraversable polynomial bifunctors can be used in this construction. I'm not going to go through proofs for these bifunctor constructions. They're pretty much the same as the proofs I went through, except you have more type parameters to worry about. But implementations are exactly the same. And so the conclusion is that all polynomial functors, including recursive polynomial functors, as long as the traverse and seek methods return in finite time and do not go into infinite loops, as long as that is the case, all polynomial functors are traversable. All polynomial bifunctors are also traversable. And you can go on, you can define a bifunctor by recursion using a trifunctor in the same way. You can say SAB is equal to some T of A, B, SAB, where T, X, Y, Z is a trifunctor. And as long as that trifunctor is tri-traversable, exactly the same proof would show that the bifunctor is bitraversable. So you can have recursion at any level, as long as it's a finite level of recursion, obviously. At some point you would have some n functor that is not recursive, and or maybe several of them, and then as long as that's polynomial, it's going to be n traversable, and then you go back and have your n-1 traversable recursive functors and so on. And so it's clear that all polynomial functors with arbitrary recursion, so that it's a tree, for example, whose branches can be themselves lists, or you can have a list of branches or anything like that. All of that is traversable. So that's a major result of this consideration. So now let me consider foldable functors. Now we know the fold operation in a standard library. It's a fold left. It turns out that the fold operation is a consequence of having a traverse operation. And later we'll also see that the scan operation, the scan left, is also a consequence of traverse operation. So how do we derive fold from traverse? The main idea is that we should take a specific applicative functor, which is a constant functor, fa equals a constant z, where z is a monoid type. And so the zip operation on this functor is just the monoid operation, which I will denote like this. And we have seen in chapter 8 that these are applicative. Now, the type signatures are much simplified now. The type signature of traverse becomes this. And this method is called foldMap. What it does is that it takes a container of values of type A and takes a function that maps each value to a monoid, and then it traverses the container and combines all these monoid values into one big monoid value. And that's, for example, aggregation, any kind of aggregation, sum over an integer list or something like that. So the general method with an arbitrary monoid, which is generic in the monoid, is called foldMap. The type signature of seek becomes simple like this. So, and that is just to concatenate all monoid values in a container into one using the monoidal operation. So this is called mconcat. Now, there aren't any more laws because the laws are about combining. Well, the identity law will be automatically satisfied, and the composition law is trivial because you can't compose these things, because you take two monoids, compose them, you get the second one. The first one is just gone. And so all these laws are trivially satisfied. There aren't any laws anymore for this foldable operation, for the fold map. There aren't any laws. All traversable functors have these operations. Now, nevertheless, it's convenient to define the foldable type class that has these operations like foldMap and mconcat and foldLeft, because you could traverse the containers in different order, and that will be different implementations. Even though there are no laws, and it's basically a consequence of traversable. So there aren't any functors that are foldable but not traversable. So all polynomial functors and only the polynomial functors are both foldable and traversable. And so nevertheless, it's convenient to define this type class because you can have different implementations of fold for different order of traversals. And finally, let me show how to define the fold method. And that's a trick where you take this as your monoid type. Now this is a monoid where B is an arbitrary fixed type, and these functions are just concatenated by composition, and the identity value is the identity function. Now, if you substitute into the fold map, into this, you substitute B to B, you get this type signature. It's a curried function with 1, 2, 3 arguments. So if you just rearrange these arguments, you see this is exactly the type signature of foldLeft. It has your container, it has the initial value, it has the update function, and it returns the final accumulated value. So monoid is gone. We have got a specific monoid here. The arbitrary monoid, that is gone. Instead we have an arbitrary type B. So if you put B before this argument, then it's not obvious where the monoid went, but it is just a consequence of the signature of traverse, where you first put a monoid in it and then you specify to this monoid. And so for this reason, every foldable has a foldLeft method, foldMap, and mconcat, and every traversable also has them. And so now we know which functors are foldable and traversable. So let's ask, are contrafunctors useful, or profunctors useful in the same capacity? Because you could imagine that you want a contrafunctor that you traverse with respect to a functor, or vice versa. And my answer to that is, after some analysis, is that they're not very useful. Here's why. Let's take a contrafunctor CA, and let's try to do a seek on it. So that would be this kind of type signature. Now, if I have a CFA, I can contramap with the pure method, the pure F. which is A to FA, I can contramap with that to get CFA to CA. So I can get that. And then I can put that into the F using pure F. So I get FCA. And in fact, there's no other way of doing this generically. Now, it seems that all contrafunctors are automatically traversable. And I could even say F doesn't have to be a functor. I'm not using map on F. I'm just using pure on F. And so it can be arbitrary profunctor as long as it has pure. It's actually applicative profunctor, or even just appointed with a pure. So it can be just like that. So is that useful? Well, in my view, it's not useful because I completely ignore all effects of F. I'm using pure of F. So whatever F I had here, I'm ignoring its effects. I'm never going to have any effectful value here either. It's going to be always a pure. So it's not very useful. And in the other direction, you can't do it. FCA to CFA. Because you can't extract out of F necessarily. Now, if you have a profunctor CA, then things are not workable. Here's why. Consider this simple example, the simplest profunctor, which is neither a functor nor contrafunctor, because it has A in both covariant and contravariant positions. And now we need a sequence function of this type signature. But it's impossible. We cannot get an F of A to A unless we somehow get an A to A first. But we can't. There's no way to extract A to A out of here. So we can't get an A. We can't get an F of A. And so there's no way to do this. So the only way to implement this type signature is to return pure F of identity here. But that ignores its argument. And functions that ignore its argument will not respect the identity law. They will not preserve information. And finally, let's try to traverse profunctors with respect to profunctors. And we find again that the only way to do that is to ignore all effects. And here are two examples. So consider this contrafunctor and this contrafunctor. Then now, if it's applicative, it means that S is a monoid. And so this type, the only way to implement is to return an empty value of F on the right, ignoring LFA. And the second example is if you take this contrafunctor and this functor. And again, you can show that the only way to implement sequence of this type signature is to always return empty option. And again, that would ignore its argument, and so it's most likely not going to be useful. Because we ignore all the effects, we never return anything that's not empty, and so on. So we are able to implement these type signatures. Let's see. I have this test code here, where I check that we can actually implement only one type signature and that it returns an empty option. And in both of these counterexamples. So take a look at this in more detail if you feel like, but I'm of the opinion right now that since all of these examples show that I have to ignore all effects, I have to return a value that ignores all the input data or ignores all the effects in the functor or profunctor F. That's probably not a very useful implementation, but there isn't any other. Also note that the laws of traversables do not actually say that effects of f cannot be ignored. They don't actually say that. So you can traverse each element once, and that's guaranteed, but then you can just ignore the effects, maybe. Well, for some functors that's possible, as we have just seen. So the conclusion is that traversable contrafunctors and profunctors aren't really so great and aren't very useful. Let's look at some examples where we use traversable functors. The first example is how we can convert any traversable functor data structure to a list. To do that, we will actually have a trick that we will define a list as a monoid, not as a type constructor, as a constant type, but as a monoid. So it will be a constant functor. To express this, I define the type constructor z, which has a type parameter b, but it's equal to list of c, where c is a fixed type parameter up here, so it's not depending on b. So this will be a constant functor, which I define like this, so it doesn't change anything. The type parameter is not used. And it's applicative as well, as a constant functor that is a monoid. So we define the applicative instance using the vzip, and this is a nil and a monoid composition or concatenation of lists. And just for fun, I want to define the monoid composition in the opposite order. So having defined this, I now have z as a applicative functor, and I can use traverse, which is this function that I defined for convenience on a traversable value. And so now I traverse f of a, which is this L of c, or probably better called. Now this L of c is of type unknown type constructor L. So we traverse it with a function that takes a value of type c and returns a list containing a single element c. The result of traversing is that for each element from the data container L, we will have a list of a single element, and then we will concatenate all these lists, because that's the effect of the applicative functor z. And we need to combine all these effects for all values in the container L. And the combining is done using the monoid composition. And so then the result will be a list of all elements from the container L. So let's see how that works. We define L like this. We have seen the implementation already. And now we define the value of this type. The value is a triple 1, 2, 3. And then we call toList in it, and the result is a list of 3, 2, 1, because we have defined the opposite order here. So if we define the straightforward order, we would have a list of 1, 2, 3. Otherwise, we have a list of 3, 2, 1. So in this way, we see that any traversable functor is a data container that can be converted to list, and the order of list elements depends on the order of traversal, which is specified by the traversal type class instance. The second example is to aggregate data from a tree by using a fold. So in fact, since fold is an operation of traverse where the applicative functor is a constant functor, here we have just used foldMap. Essentially, we don't need traversable here. It's sufficient to have foldable. We could have defined this function by folding with a list. But let's continue using traverse, just so that we understand that these are very much related to each other. So here's a definition of a simple tree type. It has a leaf of type A, and it has a branch with two trees. Now we define a functor instance in the usual way. And then we define the traversal for this tree, which is defined also in the usual way. This is a recursive construction 4. And so I'm just writing it out, but this follows from the recursive construction. If we have a leaf, then we just put the leaf constructor under F. And if we have a branch, then we run sequence on both branches. This is a recursive call to the sequence function that we're defining right now. And then we zip the results and put the resulting tuple under a branch. Here are some example values of this type. So this is a tree of integers, and this is a tree of strings. And I drew this picture to visualize this tree T2, which has a more complicated structure. The T1 is just 1, 2, and 3. It's easy to see, but T2 is not so easy to see anymore. So let's fold over T1. So T1 is 1, 2, 3. In order to fold, let's define a monoid for integers, which will be a multiplication. And let's do a foldMap with a function that squares each element. So the result of foldMap will be the product of squares of all the elements stored in the tree, which will be 1 times 4 times 9, which is 36. The third example is to decorate a tree with order labels obtained from a depth-first traversal. So for instance, this tree, if we traverse it depth first, then first we'll reach A, then we'll reach B, then C, and then D. So then the order of traversal is 1, 2, 3, 4. And so we expect these labels to be attached. So how do we attach labels like this? It's not just a map. We could certainly attach constant or a function of each of the label, each of the element, but that's not what we want. We want to attach a value that depends on the traversal. So that's the traverse. And since it depends on the traversal, we need to compute it as we go. And so that's means we need to maintain state as we go, as we traverse the tree. And maintaining the state can be done with the state monad. So we use that state monad as the applicative functor, and that expresses the effect that we are traversing with. So to visualize this traversal, I could say that we are first so let's traverse T2 since we have it on the screen. So we first traverse T2 by visiting A, and we have some function that takes an A and returns a monad value, or an applicative functor value in general. Now we then visit B and we combine the effects. So we have 4 different effects in these 4 different applicative functor values, and we need to combine them using zip. And so the result is an f of a tuple of AB here, and then it's going to be this nested tuple. So it's f of the nested tuple, and then we have to recreate the tree structure out of that nested tuple by remembering where these A, B, and C and D were in the tree, and we have to reconstruct the tree under F. So this, and I'm not going to write much more detail, but basically this needs to be reconstructed as the value of this type. Because after zipping, you would just have an f of some tuple, and you could have converted it to a list first, but then you completely lose the structure of the tree. So the traverse operation must somehow keep track of the structure of the container and recreate it after zipping. So it zips the effects, so the effects are combined linearly in the traversal order using the zip. And then after the effects are combined, the effects are monoid, always of some kind. So they are combined linearly. There's no tree structure on the effects. But there is tree structure on the values, a, b, c, d, or whatever values you get after you transform them with the function f. And so those values have to be arranged, well, that could be of type b. Those values have to be arranged into the same tree structure as before. So now we are going to use the state monad as the applicative effect. And state monad is applicative, and when you zip state monad values together, what happens is that you update the state. So each state monad value could update the state in some way. And so this is a linear sequence of effects that you need to combine by updating the state first using this updater, then using this updater, and so on in the linear order of traversal. And that's what we will use now. We'll have a monadic value make label. So we define first of all a state monad. I'm using the cats library with integer state. So for convenience, I'll call this S right now, just in this test. So I define a make label value, which is a monadic value that updates the state and returns also this value that is the previous value before updating. Okay, I could return the next value, doesn't really matter. And that's going to be the monadic value that we're going to produce for each of the elements of the tree. Now, we actually need to represent this as an applicative functor. So let me just quickly convert to my zip type class, which is my version of applicative. Of course, the cats library already has applicative instance for this, but it's easier to use my type classes because they're very small. They don't have a lot of methods, and it's easy to see what they do. So we need to define the wrapped unit, which is just the pure of the state functor. And we need to define zip, which is defined in a regular way for any monad. This is just combining the two effects in this order. We could have changed the order here, so this is a freedom, but let's just keep this order. And this function will allow us to produce a WZIP type class instance from a state monad. Well, now let's write a tree traversal. So a tree traversal we already implemented up here. So I just copied this code in. I don't think I need it to duplicate this code. So let me just remove this code. So how do we use that? So we have T2, which was defined before. Then we traverse using the effect type S. So this is the applicative functor that we have now a WZIP instance for. We have this WZIP of S. And the result type is going to be a tuple of string int. So we're adding an integer label to a string type of the tree, which T2 has. So T2, if you look at the type, is tree of string. So the function with which we traverse takes a label and performs this make label operation, which is a monadic value, and then we map. Now this monadic value returns the integer, and then we map that integer into a tuple with the previous tree leaf. This should be called leaf, actually, to be more clear. So we map the tree leaf to a tuple of leaf and a label that we get out of the monad. So now this is a value of type S of tree of string int. So this is the result of traversal. And now we need to run it. So we run the state monad on the initial value 1, and we extract the value out of it. So this is the cats library API to extract values from state monad. And the result is as expected. So it's A labeled with 1, B with 2, and so on. So in this way we can decorate a tree with labels that are computed as we go on in the traversal. The next example is to implement scan functions, scan map and scan left. So we have seen that fold can be implemented if you have a traversable, and scan also follows from properties of traversable. So scan map is something I made up. It's a method analogous to foldMap, where you have a monoid and you map your data to a monoid type, and then the result is that unlike foldMap, it's not just one monoid value that aggregates everything. You don't just accumulate the final value, you keep all the intermediate accumulated values and put them back into your container. So this is like the scan function. So how does it work? We use a state monad. Again, its state is the monoid. So initially it will be empty, and then we will accumulate the monoid state. So this is how we accumulate. We get the previous state and we set the new accumulated state, and then we get again the new state so that we have it on hand, and then we traverse with a function that is f, which is this given f, followed by accumulate. And so the result is s of z, which is a state that accumulates the z and also gives it as a value. So after traversing, we get a value of type s of L of z. So then we run it on an initially empty value, and that's what we return, extracting out of the state monad after we have run it. So here's a test. Let's use a string as a monoid. So we import the cats instance as for a standard string monoid. And let's do a scan map on T2 with no transformation. So then we're just going to accumulate the string as we go. So we get A, AB, ABC, ABCD. So that's the result of scan map. And we can also implement the standard scan left function, which is very similar, except we don't accumulate a monoid now. We just accumulate a value of some arbitrary type z. And we do the same thing as we did before, very similar code. And here's a test. So let's accumulate the length of strings in the tree. So then we will get 1, 2, 3, 4, because all strings have length 1 right now. And the last example is to traverse a rigid tree or a non-monadic tree. I don't think rigid is a is a widely used word to describe this kind of tree, but basically imagine a tree that must have all branches full, so it cannot be unbalanced at any time. It must be full. It's a binary tree that must have 1, 2, 4, 8, 16, 32, and so on elements, and no other number of elements can be in the tree. So it's very rigid in its shape. This recursive type equation defines it, and you can easily see why. So it's either A or it's the same t of A times A. So then it's either A times A or the same tree of A times A times A times A. So then it's 4 A's or 8 A's or 16 A's and so on. So it's a infinite disjunction with 1A or 2 A's or 4 A's or 8 A's and so on. So that's why this equation works. Note we don't have a construction. Well, I did not write down the construction that can generalize this tree. This kind of construction could be generalized like this, where you have a recursive equation with some bifunctor s, and the second type parameter of the bifunctor s is not LA, as it was previously, not just LA, but it's L of some RA, where R is another functor. So in this case it will be a pair, but in general it could be some other functor. And that functor must be both applicative and traversable. And if so, then I believe this construction will work as well. So this is a more general recursive construction. Let's see the code for this. So the definition of the tree type is this. It has a single element in the branch, which is a tree of the pair parameter instead. So we substitute the type parameter, which is kind of non-trivial. So we can define the functor instance, which is a bit of work because now we need to map this branch of type tree of AA. We need to map it recursively with a function that maps AA to BB, but we don't have that function. We have A to B, so we need to construct a function that maps AA to BB out of F. And the traversal is again a depth-first traversal, where the leaf is handled the same way as before, but the branch is handled differently because we actually have this kind of type, and we need to get this. So we need to use zip for f in order to pull f out of the tuple. And so we first zip the f's together like this, and this needs to be done under the b. So it's a b fa fa map of the zip. So that's going to have b of f of pair AA, and then we sequence that, so we get f of b of pair AA, and then we wrap it into the branch. So that's how traversal works. And certainly we test it. Now this is how we would create this data structure. So it's always branch, 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 and finally a leaf with a very large, maybe nested tuple. So this is why this tree is so rigid. It does not have, cannot have unbalanced shape. So that works. We use a monoid instance for integer and do a foldMap with identity to get the sum of all these numbers. So these examples indicate that we can do a lot of things with traverse, but there are actually things we cannot do using a traverse. Because traverse operation, remember, it is an operation that needs to be generic in the effect against which we traverse, in this applicative functor. So two things that cannot be implemented as a traversal, which I find interesting that this is so, are the breadth-first traversal for a tree. So imagine a tree of this shape, and you want to do breadth-first traversal. So you traverse first at this level, you get 1, and you traverse at this level, you get 2, and then you traverse at this level. Now, that cannot be expressed as a traversal with some effect, because, as I indicated here, to visualize a traversal, we need to imagine that we are computing a large linear sequence of effects into one, or combining a large linear sequence of effects into one big effect. And now, in order to express this, we would have to know, for example, here that this 2 must be 2 and not 1. Now, this effect cannot come from just recursive traversal. You cannot just take a usual recursive depth-first traversal and run some monad, some clever monad with it, and get this other traversal. Now, we certainly probably can implement it in some other way, but I don't see how you can simply do a recursive function on a tree that traverses it against an applicative functor and get this effect. And especially when you call recursively on this subtree, you need to know how many nodes will be in some other levels in some other subtree. So it's not clear how you could possibly get that information from any kind of monad or applicative functor. Now, certainly you can implement breadth-first traversal, but what I'm saying is that you cannot take some special monad and some recursive function calls and implement it so easily. I hope you can still implement it in some way that is not too bad as a traversal. Certainly, the standard way of implementing breadth-first traversal is to use a queue, where you enqueue each node, and then you enqueue its two children, and then you dequeue, and as you dequeue, you enqueue more. So that can be certainly done in a state monad, that computation. But the problem is you need a traversal which recreates the original structure. So if all you want is to fold, then you can implement fold in a breadth-first way using a queue like that. But what you need is to recreate the original tree structure, and that's a recursive structure that has a depth-first logic to it. And so that's the difficulty. And certainly you can do it with a lot of extra work. It's not just a couple of lines of code like it was for depth-first traversal. So at this point, I don't have code for this. Maybe this can be done in some clever way, but I haven't found it. And the second thing that I don't think you can do is to label depth of a tree using a traversal. So again, it's a similar problem that effects, so these are going to be effects, and obviously you need some kind of state to hold this 1 and then update it to 2 and to 3. But effects are concatenated linearly, and so it cannot be that this 3 is the same as this. You cannot avoid concatenating this effect with this one when you do a traversal, because of this linear nature of combining effects. You cannot avoid combining effects during traversal, and so there's no way to skip incrementing a counter when you do traversals. So I don't think you can easily express this kind of labeling. And this is trivial to do ad hoc as a function on a tree. But what you want is to have a generic traversal, which is generic in the functor f, and just uses the zip and combines the effects. And that's why traversals are not so flexible. You cannot avoid incrementing your counter. You cannot have logic that says, oh, here I don't increment because they're at the same level. Can't have that logic. You must combine all effects together. So I keep talking about being generic in the functor f. So let me talk about it in a more rigorous manner. So what we're looking for is to be generic in the sense that the code for traverse, as well as the code for the sequence method, should not depend on a specific functor f. It should only use the methods pure and zip, or maybe map as well, from f. And recall how we dealt with a similar problem when we discovered functors. So a functor is a data container that is generic in the type of the data that it holds. And the map function, or fmap, is a function that cannot use specific type information about A or B. It must manipulate this data blindly with no change. You take a container, you take each element of A, replace it by B, and put it back at the same place, but you don't know what types those are. And so we expressed the law of naturality for various functions by saying that fmap should commute with those functions. So you can transform first or you can transform later, and that's what it means that it's generic in the type of data. So similarly, generic in the functor f means that if we map a functor f to some other functor g, then the traverse with respect to f will be mapped to the traverse with respect to g. So we need this mapping somehow. So this cannot be. This can be formulated mathematically. I don't want to spend too much time on this, but I just want to mention this is an important mathematical development, perhaps. But this is the first time where we have seen this kind of thing, and I don't have good notation right now for this. Natural transformations between applicative functors need to be considered. So here's the mathematical formulation. We consider two applicative functors, f and g, and we consider a natural transformation between them such that it maps pure of f into pure of g, and it maps zip of f into zip of g. And then we demand that it also should map the traverse of f into traverse of g. So if we do that, well, all we do is we just say, we have a traverse with respect to f, let's apply it and then map f to g in the result. Because the result of traverse is f of something, f of some L of A or L of B. So we can map that into g of that using the natural transformation. Or we can first map f to g and then apply traverse, and that should be the same. And so this is a naturality with respect to the functor as a type parameter. So it's a higher order type parameter. It's a otherwise it's quite similar to naturality, and it's just more complicated because it's not just any natural transformation. Natural transformation by itself has laws already, and in addition to being a natural transformation, it needs to preserve the applicative properties of f, so that pure is mapped to pure, zip is mapped to zip, and the laws, of course, must hold for both applicative functors. So if you look at this notation, which is slightly made shorter on purpose by omitting various type parameters, it really looks like lifting from a function f to g into function of traversing f to traverse g. But f and g are not types, they're type constructors. So, and this is not a function, this is a natural transformation, which is a more complicated object. So when we used category theory to describe such liftings, we would usually say this is a morphism in one category and this is a morphism in another category. But a morphism, as we defined it, was always between two types. And now we don't have types, we have type constructors. So we need basically a morphism between type constructors. So that's more precisely between applicative functors. So a morphism between applicative functors, that's what we need to lift into a morphism of traversable functors. And so that requires a more general definition of category than what I have given so far, where in the definition I've given so far, morphisms were just twisted function types, but now we need morphisms between type constructors, or even more restricted ones, morphisms between applicative functors with extra properties. So category theory describes this, and a general definition of category can be given, which I'm not going to give right now, because I don't see any use for it, other than to indicate the property of naturality as being similar to previous properties. I encourage you to look at category theory at some point, but I will only talk about what I see as being useful. And so right now it is useful to think about this as a lifting, and the laws, of course, need to hold, such as identity and composition. So if we map F to F, then we don't change anything. This should be lifted into identity and composition. F to G to H mapped to composition of those mappings, and so on. So those are the rigorous forms for the naturality law with respect to applicative functor. Now, I'm not writing it out in detail because just as naturality with respect to ordinary type parameter, this naturality with respect to applicative functor is going to be satisfied automatically by any code that merely uses pure and zip. And why is that? It's because when we perform a natural transformation that maps f pure to g pure and f zip to g zip, the code doesn't actually change at all. The code has f as a type parameter, and it just uses pure and zip in the code to calls them, as we have been doing when we implemented the traverse instances, for example. So let's see, here, for example, we are using zip. This zip is from the functor f, but f is a type parameter. So if we now apply a natural transformation from f to g for some other applicative functor g, this code doesn't change at all. It still uses the zip, and we have the condition that this natural transformation that maps f to g, it maps zip to zip and pure to pure, and map to map, of course. That's the naturality of natural transformation. So our code won't change, and our code therefore is invariant under this natural transformation. And so it's automatically going to satisfy naturality with respect to the type parameter f. And it also will automatically satisfy naturality with respect to type parameter a. And that's why we never need to check these laws explicitly, or even spend so much time writing them explicitly, because they're useful sometimes when you reason about code and prove some other laws, then they're useful. But for coding, for implementing, you always have naturality automatically. So this concludes chapter 9, and here are some exercises for you to implement. Let me just comment on this exercise. So I don't want you to prove laws by hand for this functor t. It's cumbersome, but instead use constructions. So we have proved general constructions. So if you express t as a recursive equation using some bifunctor s, and you show that the bifunctor s is bitraversable, again using constructions, of course, then you don't need to do the proof yourself. The constructions already prove once you have found them. And similarly, for this construction, you don't need to prove anything by hand. This exercise is a little different, but you can try to prove this extra construction that I mentioned, this one. but it's very similar to other constructions, and so it's not necessarily part of this exercise. This concludes chapter 9.